morning, or at least 1 or 2 tomorrow morning. So for this talk, we have from Nate Stemen, sorry, about noise-resilient quantum computing with Python.
All right. Well, thank you everyone for being here today. I'll be telling you a pretty high-level overview as to kind of where we're at in quantum computing, and also why Python plays a role in that. And there'll be a little bit of quantum computing, about 3 or so slides to hopefully get us all up to speed, and then we won't need to understand all of the details, but that will inform kind of where we're at as an industry, as a technology, and as a science. My name is Nate. Just a little bit about me, besides the fact that I don't really have a professional picture besides the one that's in the program, but it has me with a buzz cut, so that's quite a long time ago. I have a master's degree in mathematics. I used to work at Overleaf, so if you've ever done online LaTeX, maybe I played a role in the autocomplete functionality. So I used to be a bit of a web developer. Now my role is somewhat that of a research engineer, a research scientist, and I work to support the open source community within quantum computing. I'd say I'm a big open source fan that I got into mostly through LaTeX, and again, open science as well. And this is my first SciPy, so it's been a really great experience so far, and I'm looking forward to learning more about what I've already learned. Okay, so just a quick outline. We'll do a very, very brief introduction to quantum. I'll talk about why noise is kind of the big problem in quantum computing right now. I'll talk about why Python is playing an important role in the development of quantum computing as a whole, but in particular for fighting the problem of noise. And then I'll end with some thoughts about where does Python go in the future of this emerging technology of quantum computing. So first, just to start, what really is quantum? So at the very basic level, our classical computers are built on logic circuits, and they manipulate zeros and ones. And they're built out of things like and OR and XOR and many more logic gates. In quantum, the situation is relatively similar. We have slightly larger set of operations that we can do on quantum information, and those are called unitary operations. And importantly, though, classical computing is not inherently irreversible. So if I give you the OR of 2 bits, you can't necessarily tell me what 2 bits I ORed together to give you. And quantum computing, the theory of quantum mechanics, the actual physics, tells us that everything has to be reversible. So there's no such thing as destruction of quantum information in this pure sense. So on the right is what the objects manipulating quantum information look like. They're called quantum circuits. And importantly, at the end, there's something that happens which is usually a destructive measurement. So you destroy the quantum state to get access to some information that's hidden in there in some sense. So the one thing I didn't tell you about in these pictures is what actually is quantum information. So the building block of quantum information is that of a qubit. So in classical computing, we have zeros and ones, and we operate and we do computations thereon. In quantum computing, the situation can kind of be seen as a generalization thereof, where instead of just being on the poles of the sphere with a 0 or 1, you can be anywhere on the sphere, representing some sort of data. So you can understand that the operations that we have access to in quantum computing is not just change a 0 to a 1 if you're just operating on one bit, but you can modify your state anywhere on the sphere to anywhere else on the sphere. So you have very complex operations. And this kind of hints at why noise in quantum computing is a much more complicated problem, because if I have an operation that I'm trying to do that's manipulating a point on a sphere, I can end up anywhere else potentially on the sphere. In classical computing, I go from 0 to 1, and maybe I make a mistake and I end up back at 0. In quantum computing, I try to do some complex rotation around a specific axis, and maybe I over-rotate by some some epsilon. And then on the right side is what happens when we do measurement. So if you have some quantum state that's a point on the sphere, and I go to try to read out information from it, that is, I look at the system itself, it's going to collapse to either the 0 or 1. And so that's a kind of counterintuitive thing. So how can you actually do more computation, or how can you hope to do something that's more powerful on a quantum computer if every time you look at your system, it's either 0 or 1 or some complicated bit string? That's the part I'm not really going to explain too much today, is how people actually do the algorithm development of using the complex physics that are at play to actually solve problems. But you're going to have to trust me that smart people have done that, and we have algorithms, we have quantum algorithms that utilize the physics that are happening here to solve problems, at least in theory, more efficiently than that we can do on a classical computer. Some of the highlights of those algorithms are the first and most famous one that was written about is called Shor's algorithm, and it's an algorithm to factor large numbers. And if you know much about cryptography, you know that that's a difficult problem, and it's the basis for which many crypto systems rely on their security. The problem of factoring numbers is difficult, therefore we can build a crypto system on top of it that is very difficult to be broken on classical computers. Quantum computers pull that into question, and so that's why we have things that are now called post-quantum cryptography or quantum resilient cryptography that the government is slowly rolling out. Okay, so that's a bit about quantum computing as a technology. But what does it actually look like in practice? So if someone is programming a quantum computer, what does it look like? So this is like the hello world example of quantum computing. This is the program that one could write to generate what's called a Bell state. And this is a state that has some strange spooky action at a distance, if you've heard that before. And so again, without getting too far into it, what's happening here? So on line 3, we're defining a quantum register, and we're saying, please give me 2 qubits, please. On lines 4 through 7, we're saying, define a circuit, and we're only putting 2 operations on the circuit. The first one is called an H gate or a Hadamard gate, and it's going to put the first qubit in a superposition, and then the second gate is a controlled NOT operation, and that's going to entangle the 2 qubits together. And I don't want to go into the details here, but the point that I'm trying to showcase here is that quantum programming right now is operating on registers. When we're doing classical computing, most of the time we're not asking for, at least in Python, we're not asking for, please give me a register of this size. I need this much memory allocated. In quantum computing, we have to do this very explicitly because the devices that we have are relatively limited. There's a very small number of qubits, and also the field just hasn't been around long enough to develop what are the appropriate abstractions that we can kind of push these quantum circuits lower so that we don't have to write them directly. But this is where we're at. That said, as scientists, the goal is to think about a quantum computer eventually as somewhat of an accelerator. So right now, most computers or most workloads get distributed across different types of processing units, CPU, GPU. Maybe if you're doing something really advanced, you have a TPU or a data processing unit. The goal is that in the future, you write some complicated workload that you need to send to an HPC. To a supercomputer, and there's some really smart compiler that says, this part of your workload is actually amenable to the things that quantum computers are really good at, and it'll send that part of the computation off to the quantum computer. Now, quantum computers right now are not quite chips. The quantum computers, as they exist today, are more like humongous laboratories, and the picture that I've drawn here in the center is a quantum computer, or a diagram of a quantum computer that is called a superconducting quantum computer. So it uses superconducting circuits as the basis of quantum information. And there's a really cool thing about this particular quantum computer, this type of quantum computer, is that where the qubits live, which is at the bottom of the diagram here, you're at a temperature of very close to 0 degree Kelvin. So for reference, outer space is something like 2 point something degrees Kelvin, and down at the bottom of these refrigerators, you're at 10 millikelvin, so negative 460 degrees Fahrenheit. So it's extremely cold, and they pump out all of the air and vacuum it as much as possible so that the quantum systems that are underlying the system and that are acting as our quantum information have as little to interact with as possible. Because again, any interaction with the environment will likely cause an error in your computation. Okay, so some brief takeaways from quantum, like what I've talked about so far. So we're in the very early days of quantum computing. Like I showed, we're programming with quantum registers, and we're directly applying what are the equivalent of quantum logic operations. Quantum noise is also a lot more complicated than just bit flips. Like I said, if you're on this sphere, you can go to any other place on the sphere, potentially by accident. So part of the power that comes with quantum computing is also part of its potential downfall. It's very easy to make faults in your computation, much more so than in classical computers. In a classical computer, the probability of a fault happening at some point in an operation is something like 10 to the negative 15. It's extremely low that faults happen during computation. But on quantum computers, as we currently have them, that similar analogous error rate is something like 10 to the negative 3, 10 to the negative 5. And so errors are happening a lot more frequently. So the thing is, though, error correction has been around as a theory since at least the 80s. So the general premise in error correction is maybe you want to send some message to a friend, and maybe that friend is you at a later date, and so that means just you're storing data. And so let's say I have 4 bits I'd like to send along some channel, but when I send it along that channel, there's some probability that each one of those bits gets flipped. So one of the most naive ways to encode this information more reliably is just to say send the message 3 times. Then each bit can be potentially corrected by just taking a majority vote of what was the most common bit that was received. A slightly more complicated way to do that is to create parity bits, and so you take a parity of each one of these subsets here. So say bits D1, D2, and D4. You take the parity of those and you attach that to your message and send it along. And then the receiver can then use these parity bits to again correct, and you save quite a bit of space by doing a more advanced method like this. And this is an example of classical error correcting code that is very similar to what's used on a lot of used in classical infrastructure today. For example, if you scratch a CD and you are still able to play it, even though you've destroyed some information on the CD plays because the information is stored redundantly. Now, the situation is kind of good because we can employ a lot of the theory that we've developed in classical error correction to quantum error correction, but because of the challenges, because of the fact that quantum errors are much more nasty in some sense than classical errors, it's a lot more challenging. And so this picture on the left, without going into too much detail, is each one of these dots, the blue and yellow dots, are physical qubits, and this entire patch represents one logical qubit. So we're using something like 50 qubits to represent one logical qubit. And that's okay. We've had some experimental demonstrations of error correction on real devices, But our current devices have on the order from 100 to 1,000 qubits. And so if you're spending 50 qubits just to create one logical qubit that has a better error rate, then if you have a device that has 100 qubits, you only have 2 logical qubits, which is maybe an important scientific achievement, but it's not anything useful to do computation with. And just for reference, on a classical computer, you can simulate, on my laptop, you can do something like 30 qubits with a performance simulator, and in a HPC facility, you could simulate something like 50 qubits. So we really need, to do something useful with these devices, you need a decent sized number of qubits. So quantum error correction existed. It's been around since quantum error correction in particular has existed since the 90s. Once these smaller devices started coming online and it was clear that we can't just scale up this technology very quickly, we started thinking we need techniques to deal with errors without the added overhead of additional qubits. So the idea behind quantum error mitigation came into play around 2015, and it's been quite a popular idea since then. So this is just a smattering of papers that have come out since then. And so these are techniques that use not qubits as additional resources to help defeat the noise that's happening on quantum computers, but things that are relatively cheap in comparison. So classical compute is very cheap in comparison to quantum compute. So if we can use the classical compute in some way to help aid the quantum compute, then that's a win. So that's what quantum error mitigation asks. Can we do that? And just to give you a flavor of a particular error mitigation technique, one of the most conceptually simple examples is that of zero noise extrapolation. So if we suppose we have a circuit that we're interested in running, a quantum circuit that we're interested in running on a device, you can run that particular circuit, but then we ask, okay, we can't scale noise back. You can't prevent noise from happening, but we can try to make more noise happen. So you modify the circuit in some way. So this is 2 in this drawing, and you run that circuit. And then you try to add more noise, and you run that circuit. And it doesn't matter exactly how you do that, but if you're able to do that, then you can use these data points that you've probed at a higher noise level to extrapolate back to what happens when there's no noise. And going to the physics, it's basically running it's running your computation with larger and larger noise, and trying to get rid of that. When you do the extrapolation, you're extrapolating back to your ideal von Neumann equation. Okay, so this is just to give a sense of what these kind of error mitigation techniques do. And so in 2020, after, there's probably 5 to 10 existing error mitigation techniques that exist in literature, this project MITIC got started. So MITIC is the project that I now maintain, and it is a toolkit for implementing error mitigation protocols. So this first diagram on the left is a diagram from the original white paper that was published. And so here there are 3 techniques that were originally implemented: zero noise extrapolation, and then PEC and CDR. So there was 3. Now there's something like 8 different error mitigation techniques that we support in our package. So why did we originally choose Python to build this particular package? So one, obviously there's a rich scientific stack, and so we don't need to go about building a lot of the existing tools to do numerics that we need. But potentially more of a reason was a lot of the most popular quantum SDKs, so the things that you write quantum programs in, already exist in Python, and the reason that is likely because of the first point here as well. It was also quick to implement many of these techniques just because Python is as ergonomic as it is, and it's close to IDEA, more so than other low-level languages. And really the goal here was to get people to hopefully contribute to the package, provide researchers a structure so that if they are doing research in error mitigation, they can propose their technique, and if they would so be inclined, they can implement their technique in our package without too much work. But quantum is changing. So the organization that I work for, every year we run a quantum open source software survey. Think about it as the Stack Overflow survey, but specific to people in quantum. And so one of the questions we ask people is, what programming language are you using? And this is the plot on the left, 95% of people say they're using Python. So just to give you a sense of how dominant this language is in this field. And on the right, we asked, what are you hoping to learn, or what do you consider the most promising for the future? And the number one answer is Rust, with 48% of people interested in learning Rust or find it most promising in the future, followed shortly by Python. I guess what is this hinting at? And as quantum has gone from in the lab and more of a science to something that is potentially a future technology, things have gotten a lot bigger. The quantum programs that people are interested in running have gotten a lot bigger. And so when you think about feedback loops, quick development, or not necessarily quick, but it's very important for developers to have fast feedback loops when writing and working on quantum programs, just like it is any other type of program. And so when someone writes a quantum program and they need to do testing on it, whether it's simulate it, whether it's compile it, regardless of what that is, it needs to be a relatively quick loop. And we're reaching this point in the field where Python handling, for example, the data structures that's underlying a quantum circuit that's 100 qubits and 10,000 gates long is just becoming inoperably slow. And so there's parts of this ecosystem that I'd say Python is thriving, and it's doing really well supporting the needs of the community. And there's parts where that's not necessarily the case. And what we've seen over the past, particularly like 2 years, is a lot of the most popular SDKs, they're starting to do replace some of their internals with lower level languages, C++ and Rust most commonly. So the future maybe looks something a little bit like this, where we have this Python interface, but under the hood there's something else happening. At least this is what's happening with Qiskit, which is the most popular quantum SDK at the moment. They're rewriting a lot of their internals in Rust, but again, maintaining a Python interface to make to keep the ergonomics of writing quantum programs easy. The other thing that's interesting that's happening in this space is at the same time that we're reaching points that we're thinking about, do we need to rewrite certain components to become more performant? Python itself is becoming more performant, and so there's some ways in which certain things need to be rewritten, and there's some things in which the improvement performance gains in Python are allowing us not to worry about that too much. So just very briefly, I just want to touch on the organization that I work for. So it's a nonprofit. We work to grow the open source ecosystem within quantum. We give grants to people who are kind of like explorers in the quantum open source space. So it's $4,000. It's no strings attached. It's to kind of explore new ideas. We've given over 100 by now. We do a lot of our own research, so the error mitigation toolkit is there to function and to power further research. We do benchmarking of quantum computers. A lot of quantum companies, it's not necessarily easy to trust everything they say, because they obviously want to be the best and to be seen as the best. So they publish things that seem favorable to them, and so we want to provide some more honest and third-party benchmarks. Underlying a lot of that, we have a pretty thriving community. So there's a Discord. It's all available on our website, unitary.foundation. We run a weekly journal club, the software survey, and then we run a hackathon every year where we help get people paid by contributing to open source quantum. Okay, so just some closing thoughts. Quantum is really weird, but hopefully it doesn't have to be that weird if we think about it as like a potential accelerator. Under the hood, yeah, there are lots of weird things happening. Noise is really our biggest problem at the moment. And Python is really helping us solve and implement those techniques which researchers are coming up with to aid in the problem of noise. And with that, thank you. Here's how you can contact me if you so choose.
All right. So a few questions in Slack. Definitely time for more if you've got some questions you want to ask. So first, a very important question. Did you manually draw your slides, or did you use some tool or package to do that?
No, I drew everything.
Nice.
Yeah. I had quite a good time, actually. It's the first time in a while that I've drawn some slides, and after messing around, I've made a lot of slides with LaTeX. I've made a lot of slides with PowerPoint, and it's nice not having to use my arrow keys to move things around. I will say that.
I was a little surprised it wasn't like a Beamer presentation or something. I don't know, that guy. All right. Can you elaborate more on the reversibility of quantum computing operations? Since measurements of a quantum system collapse any superposition of states, I'd expect the operations to be non-reversible, just like in the classical case.
Yeah, okay. I did gloss over the fact that computation in quantum computing is reversible. The measurements are not reversible. That is one of the really strange things that happens in quantum. If you want to know more about it, it's the measurement problem. So we don't really have a good philosophical understanding of the theory tells us that everything is supposed to be unitary, and unitary means reversible. But then when you talk about measurement, that hypothesis or that goes away, and you no longer have that reversibility. So I can't really say much more on it besides it is an open philosophical problem.
All right, so just moving in order, a potentially silly question, although probably not, but no. Would quantum computing be able to work on a space probe or on a satellite? How do we deal now with cosmic rays, energetic particles, et cetera, that would impact things?
So cosmic rays do cause strange errors in quantum computing. It causes very correlated errors. So if you have a cosmic ray come through your quantum chip, you're going to get a string of errors that happen in a row, basically. And there are many quantum error correcting codes that we hope to use in the future. Not all of them are very good at protecting against this type of correlated error. Most of them are very good at protecting against random errors, which is the thing that is happening when cosmic rays are not interacting with your device. But we do know of some codes that are that can potentially correct those type of errors. They're definitely less studied than others, though. So to answer the question, though, can we put a quantum computer in space? Probably, but I don't know what the benefits of that would be. But that's not to say that we can't. It's just I genuinely don't have a reason why we would want to do that.
Is the transition you see in Qiskit,
yeah,
and others from pure Python to Python with Rust, or from Python with Cython, or C to Python with Rust?
Oh, wait, what is the question?
The transition you're seeing, I think, talking about Python and Rust, is it from pure Python to using Python with Rust, or is it from pure Python that's with Cython or C to Python with Rust?
Yeah, okay. So at least with Qiskit, it was largely a pure Python project, and now it is a Python with Rust project. I don't know, why Rust was chosen over using Cython. Or other alternatives. I mean, the the aesthetic of using Rust is it's pretty good, but so yeah, that's maybe a big part of it. But the one thing I want to highlight with that question is there is a large community effort with Qiskit, and as you shift away from Python with lots of internals in a lower level language, you do have a bit of a harder time maintaining a community of people who can contribute to that package. Anything that is related to quantum already has a higher barrier to entry because of the large physics background or some amount of knowledge that's needed. And when you now start adding Rust on top of that, you're just losing the number of people who can contribute. So it's a bit of a trade-off when you think about maintainability.
There's actually another question which I think is a good follow-on, which is, can you point to an example of code moving into Rust that you think would have been better left in Python based on recent improvements in Python?
I don't have an explicit example. I feel like I would need to do a little bit of searching to find something like that. Yeah, sorry, I don't have a.
Would there be? I mean, maybe you don't have an example, but do you think it would be worth actually taking something back to Python now that?
Yeah, I mean, as long as it's not like too interpreted into the Rust or whatever, like rewrite. If I think if that makes sense for the maintainability aspect, it seems like it would be. But I don't know. I guess I'm not working explicitly on that project, so.
And I guess just one other, we have time, another minute or two maybe, but just a question is that, I can't remember the name of the package that you presented that you were.
Mitic.
Yeah. Has that been submitted to JOS, and if not, why not?
So it is published in the Quantum Journal, which is very amenable to publishing things in open source, so other tools. It's just maybe more niche. But I do know that some of the other tools that we have funded as an organization, given microgrants to, have published in JOS.
Yeah, I've seen some.
So we did not publish in JOS, but it is published, and I think it was like, as long as it's out there, that's enough.
All right, let's thank our speaker again.
Great, thank you.